We're live?
Yeah.
We are live. Okay. Start my timer. Hello, everyone. Welcome. Everyone is well eaten. You've had your lunch, right? You're ready? You're not going to take a nap on me? Did you get your Red Bulls? No? Okay. All right. So this is actually like 45 minutes worth of material that I'm going to condense down to about 25 minutes. So I'm going to try to go a little bit fast here, but I'll stick around at the end for any questions that you might have. We're going to talk about optimizing AI in several ways: efficiency, relevance, and cost savings. My name is Jesse Hall. I'm a staff developer advocate at MongoDB. You might also know me from YouTube as Code Stacker. If you haven't heard of my YouTube channel, you can go ahead and subscribe. I'd appreciate it. Now, even though I do work for MongoDB, this talk is not about MongoDB. It is technology agnostic. So you should be able to use this in whatever stack you're using. So brief agenda, but we're going to skip past that. We're just going to dive right in. So you've heard of this thing called GPTs, generative pre-trained transformers. These large language models perform a variety of tasks, from natural language processing, content generation, and even some forms of common sense reasoning. And so these are really the brains that make our AI applications smart. This is the underlying technology for that. But there is a catch. These GPTs, they have limitations. The main limitation is their static knowledge base. They only know what they were trained on. And so that is one of the issues. We know that there are some implementations, integrations now that allow them to search the internet to find more relevant information. But how do we know that that information that they're finding is relevant? They can also hallucinate. They just make things up sometimes. So how can we minimize that? And they can't access our proprietary data, our domain-specific data, and that is a really big limitation. And so how can we fix these LLMs? Because creating a new LLM from scratch is very not cost-effective, right? It's very expensive. So how can we fix that? That is where RAG comes in, Retrieval Augmented Generation. You've probably heard this in a couple of other talks here earlier today. We're going to quickly kind of get an overview of what RAG is so that we can understand what we're trying to optimize for. And so let's go straight into the first thing that we need to understand about RAG is our vectors. So we have this vector here, a quick brown fox. That text equals this array of numbers, these floating point numbers. Those are vectors, vector embeddings. So these vectors, they are a numerical representation of data. They are basically just an array of numbers, right? And these are coordinates in an n-dimensional space, where n equals the number of items that we have in that array, right? So however many numbers we have, that's how many dimensions we have. And you might also see these referred to as vector embeddings or just embeddings. So here is a real-life example of vectors in use. So you go to Home Depot, you're looking for light bulbs, you ask one of the employees there, where can I find light bulbs? They say, go to aisle 15, bay 30, right? So that is a 2D vector in real life. And also notice that all of the light bulbs are kind of strategically placed near each other so that they're easy to find. It's exactly how a vector database works, and exactly how vector embeddings work. They are strategically placed in a way that's easy to find using vectors. And so again, what makes them so special? Vectors allow semantic search, similarity search. And so they find things that are contextually relevant and not just keyword matches. And then these data sources, they are not limited to just text. You can create vector embeddings for text, images, audio, video, and so on. So these can all be converted to vectors, but how do we do that? How do we go about converting these to vectors? We use this thing called an encoder. And an encoder defines how the information is going to be organized in that virtual space. And there's different types of encoders. So there's encoders for text, for images, video, and so on. These are, you'll also hear them referred to as embedding models. So these are LLM models that are meant specifically to create these embeddings. There's going to be some QR codes throughout this, so if you have your cameras ready, you want to learn more about choosing the best embedding model for your LLM application. This you can dive a little bit deeper here to learn more about choosing, because there's so many different embedding models out there. All right, I'll just go back. I see a couple of cameras still up. I'll wait for the cameras to go down, and then here we go. All right, so what does this look like in practice? So we've got our private data, our custom data, whatever that might be, and then we split that data. If it's a long article, we have to split that down into chunks, and then we create embeddings from those chunks, and we store those chunks in our vector database. And again, this could be text data, it could be images, it could be video, and so on. And so this actually, this looks simple, but there's actually a lot to this. There are, in fact, chunking strategies. So you have to pick the right embedding model, but you also have to figure out what is the correct chunking strategy for whatever it is you're creating embeddings for. So here's another resource on how to go about choosing the right chunking strategy for your LLM application. All right, I'll give it just one more second, and then here's the rest of that. So we've got all of our embeddings in our vector database now. We can now accept user queries. So the user has a prompt, and what we have to do first with their prompt is create vector embeddings for their prompt. So we want to put their prompt in that same virtual space as our custom data. So we create embeddings for their prompt. We figure out, we send that to our knowledge base to use vector search to find the most relevant chunks from our knowledge base, and then that outputs the chunks, and then we send that to the LLM. So we're kind of intercepting their prompt. We're intercepting their prompt, we're adding some extra context to it, and then we're sending it to the LLM to answer the question. And so that is RAG right there in a nutshell. Let's talk a little bit about search and retrieval. So search and retrieval is very similar to RAG. This is a normal RAG pipeline at the top. You've got your database, and you're searching for the similar information, and then sending that to the LLM. How can we improve this RAG pipeline? So the first thing that we could do is we could add a filtering stage. So what if we had extra metadata in our database that allows us to define which chunks we know are relevant to this query and which chunks aren't? And if we could filter out a bunch of chunks before even going into vector search, that would save us a lot of time, and it would result in lower latency and cost savings as well. So this is one of the times where I'll talk about MongoDB. It's a great general purpose database for saving that metadata alongside your embeddings in the same database, and not having to go back and forth between an operational database and a dedicated vector database. So eliminates a lot of that need there. So the next step, we go on to the regular vector search, just like we do above, but let's add to that. Let's add a scoring step. So the scoring step, we could incorporate maybe some user feedback. We could rescore these chunks to optimize for certain keywords. And then after that, we could add an ordering stage. And so an ordering stage, in that stage, we could re-rank, maybe using a re-ranking model, because we have seen, there have been some white papers written about LLM's context windows. They tend to concentrate on the top of the context window. So the bits that we send it first, it concentrates more on that and not so much at the rest of it. So we want the most important information to be at the top of the context window. So let's take a look at each of these stages of this 4-stage RAG system. You're not going to see this 4-stage RAG system anywhere else. This first stage is the filtering stage. Again, if we have some metadata that we can filter out certain chunks before we send that to the vector database, you can see here that a filtered vector search is going to be more accurate, and it's also going to be computationally less of a load, because we're not sending all of the chunks to the vector search in order to search through. And here is an example. Here's a real world use case. So the yellow query vector, that is the user's query and the vector similarity to the documents around it, right? And so let's say that we have a movie database. So the user is wants to find movies that have an IMDb rating greater than 7. And they also want to return the top 2 results. That's what K is. K is returning the top 2 results. So in our metadata, in our database, we have IMDb rating as a field that we can filter. And we say, only send embedding chunks that have a filter greater than 7, and then send that to the vector database. So that's going to result in those 2 being returned because they have an IMDb rating greater than 7, and they are the closest to that user's prompt, to their query. And so again, that is going to be less computational load and more accurate, and less latency as well. So there are a couple of different search methodologies. We have talked about vector search in the context of RAG, but there are other search methodologies. One of them is lexical search or keyword-based search. Now, usually, in almost every RAG situation, you're going to use vector search, able to reorder them so that the LLM has the most relevant information at the top of the context window. So a re-ranked hybrid search, again, is going to be more accurate, but again, more computational load. So here's what that looks like. We take our results in whatever order the LLM decided to give them to us, because it doesn't really know what order we want them in. And we send it through another LLM model that is specifically designed for re-ranking. So these models actually calculate the relevance between query document pairs, and they're able to tell which ones are the most accurate. And so now we have that 4-stage RAG system. We've gone from a regular RAG system, which is very accurate, sure, but we've taken it to a much more accurate system now through all of these different steps there. So let's move on now to the saving money part. So we've made it more accurate. How can we, in production, save money? So we're going to talk about 2 things. We're going to talk about prompt compression and vector quantization. So prompt compression, we have many different prompting strategies. Prompt engineering, that's a thing, right? So most of these prompts that you look at, they're like walls of text, huge amounts of text that we're sending to the LLMs. And because of this, the context windows of LLMs have continued to grow and grow and grow. But tokens cost money. It costs money to send all of that text to the LLM. It takes the time to process it, and then it has to return the results from that. So we actually have seen prompts that have 100,000 tokens, even 1 million tokens. It's like passing an entire novel to the LLM in one pass, and that's not very efficient, especially when you're using it through an API call. And it can become very expensive sending all of that over the wire. And so what we have here is 500,000 tokens that costs in this input, and then we're outputting 4,000 tokens. Very large context windows. That's kind of the norm now, but how can we change that? So we're going to talk about prompt compression. So this is the process of reducing the number of tokens that we are passing into the LLM. So how do we do that? Our goal is to have the same output. We want to, whatever the uncompressed prompt is and whatever the output is, we want the compressed prompt to produce that same result. And so here's an example. So we have the original text at the top, and then the compressed text. You can see that the compressed text has the essence of the original text. It's just using less words. And so, we do have to be careful here. Too much compression is going to result in less accurate results. So this is just one of those dials that we have that can help us save some money there. And so what we can see here is we can go from a prompt that is 50,000 tokens, and the output is going to be 4,000 tokens. We could compress that down to 10,000 tokens, and we're still going to get that same prompt. And again, this is one of those things that you just kind of have to test in your environment and see how much compression is too much and how much is just enough. And so for that, in evaluating your applications, I've got another resource here for you to help you evaluate your LLM applications and to see, making sure that you're as accurate as possible, but without turning too many dials too high, right? All right, wait one more second for the phones to go down. All right, so the last thing that we're going to talk about here for money savings is the reduced representation vector quantization. That's fun to say. This is basically math. This is a mathematical way to reduce the size of embeddings on disk and in memory. And so prompt compression helps us save money when we're interacting with the LLMs. Vector quantization helps us save money when we're storing those vectors and using them on our servers. And so if we look at this, look at in the memory requirements for indexing these embeddings. If you're using an embedding model that is 1,536 dimensions, that one embedding is going to take up 6 kilobytes of RAM. If you're using 768, that's going to be 3 kilobytes of RAM. Scale that up. What does that look like? If you're using the 10 million, if you're storing 10 million gecko vectors, that is going to be about 30 gigabytes of RAM. If you're storing 10 million 1536 dimensions, that is 60 gigabytes of RAM. It goes up 400 for that one. And can you imagine 800 gigabytes of RAM needed for 130 million 1536 dimension embeddings? It's like it ramps up pretty quickly. I mean, I don't know who's running a server that big. So you have to optimize for these things. So how does quantization work? What does it do? How does it actually work? So we have a quick brown fox here. In our array, we have these 32-bit floating point numbers, right? So basically, quantization just converts it from floating point to integer. It's kind of like taking this image here. We want to be able to represent this image with less data, using less data, but still recognize what is in the image. We could do that by changing it to grayscale. We don't need the color information, so we can make the size smaller, but we can still tell that that's a cute puppy. So it's kind of like that. We take a quick brown fox and we go from floating point to integer. And so there's a couple of different types of quantization. So there's scalar quantization, which takes the minimum and the maximum values in your embeddings, and then it creates evenly sized buckets, and then it maps each one into a bucket. And this is kind of what that looks like. So we've got the minimum and the maximum in our embeddings. We create our buckets, our bins, and then we just map each one into a bin. And we keep repeating that process until we have our scalar quantized vectors. Another version of this is binary quantization. So this one is much more dramatic. We're going from floating point to binary, a 0 or a 1. And so in this one, we take the median value, and if it's above that, it's a 1. If it's below that, it's a 0. So pretty simple process there. We just kind of go through here and assign zeros and ones. But take a minute here. Like we just went from floating point 32 bits, and so we have significantly reduced the information that we have here, right? Floating point number is going to represent a lot more information than a 0 or a 1, right? And so we do want to recognize that, like we are losing information. But if you think about this, you're starting with 1,536 dimensions. In most cases, you probably don't need to the full fidelity of those vectors in your use case. So the question is binary quantization too much for you? And if it is, use scalar quantization. Either way, we have to find a way to reduce the size of these vectors, these embeddings on disk and in memory, specifically in memory. This is also going to improve latency because it's going to be quicker to process as well because we're reducing the size again. So that is the end of it. So there's more to RAG than just a nearest neighbor search. You should filter using metadata to help reduce the computational load. And then full text search also plays a role in RAG. It can help with accuracy. Use a re-ranking model to make sure that you have the most relevant information at the top of your context window. Make sure that you're not compressing too much. And then quantization can make you rich, or not really, just save you some money. Yeah. Okay, so last one, if you want to see what example of an AI stack looks like, This example doesn't include MongoDB, of course, but and if you want to connect with me, I'm CodeStacker everywhere. So thank you. Sorry for talking so fast too. I had 2 minutes left. I have 2 minutes for questions if you want.
I think it probably is, but just for sake of, do you think it's feasible for an LLM to a single LLM to do all these stages like on its own?
A single, no, because each one is really designed for a specific use case. Like it was made for that use case, and so you need an LLM to answer a question. You need an LLM to like specifically re-rank. You need a specific one to do the embeddings. And if you look at how many different models there are out there, and there's so many different use cases, right? So again, there's one of those resources to help you choose the right embedding model or the right model for your use case. I don't think there's ever going to be one LLM to rule them all, though. They're specifically trained for specific things.
Yeah. So the one with actual brain using the AI as a tool.
Mm-hmm.
Okay.
Yeah. Any other questions?
Are you managing the consistent prompt correction?
Yeah, so if you have, let's say you have a documentation website, you actually need to, in your testing phase, and that's in one of the articles, come up with like 100 questions and answers that you should return, right? And then start dialing your compression and your quantization dials and all those things until you start getting bad answers, and then turn it back up until you start getting good answers again. Yeah, so you have to come up with some predefined questions and answers so that you have some testing, a way to know that it's giving you the right answers. Yeah. All right, thank you all. If you have any other questions, I'll stick around for a bit.